I hope you can see the screen. Is that correct?
Yeah, it's okay. Thank you very
Yes.
much.
Okay,
Yeah.
good. So I'll talk about our solutions like Volatek's software suite for aerial solar field inspections. So it's all about drones again. So I saw some things that will come up here again regarding drone inspections for solar fields. So who are we? We're Volatec. We're a spin-off of the German Aerospace Center. We were founded in 2020, and we provide software as a service services, for the inspection of utility-scale solar power plants. We have both markets. Like, we started in concentrating solar power. We cover now more than a quarter of the global CSP installed capacity. And we entered the PV market, where we can and have already clients, and we're working there since, like, let's say 3/4 of a year or something. Our focus is on innovation. We have a very strong focus on automation, repetition rates, which is more important in CSP than in PV, but we transfer all those learnings to the PV. So I'll go into the details to the agenda now. So first of all, I'll give you a little bit of an overview of the two technologies, CSP and PV, just to make sure, or just to let you know that these are two very different kind of things. Especially what to look for is different in those two technologies. Then we'll analyze a little bit the markets, like for inspection. Then I'll go into details on failure detection in both technologies, and also let you know where the challenges are and where we apply AI. Then how do you work with us? Like, how do customers work with our software? So we could walk through data acquisition, the data processing, and also the displaying of the results. And then I'll give a little outlook, and we have the same question and answer session in the end. So CSP, I don't know, most of you might have heard of it, especially in Morocco. It's a big thing. Like in Ouarzazate, there's a few plants, and there's even more plants throughout the country. I've visited a few of those. So it's 8 gigawatts in total global installed capacity. And the main advantage over PV is that we have the cheap storage option. So basically, you have mirrors that concentrate the sunlight to produce heat. And this heat can be converted to electricity, or increasingly it is being used as direct process heat. And plants are coming up that are a hybrid model between PV and CSP. And prospects are pretty good, although it has been halted quite a few years now. But as soon as the dispatchability in electricity grids becomes more important, our guess is that CSP also becomes more important again. And it can also be used in decarbonizing industrial heat. And here in the video, you can see at night times, you can keep on running the turbine to produce electricity, which in photovoltaics is much more expensive, because you need to use batteries of some kind, like electricity to electricity batteries, which is much more important than just a big heat storage. PV, in contrast, is much more successful, especially during the last years. 1,500 gigawatts, I think, in 23, it's rapidly growing. So don't take this number. It might have been much higher already. So you produce electricity instantaneously, use diffuse and the direct irradiance components, whereas in CSP you only use the direct irradiance. And about 50% of PV installations are utility scale projects, where you would use PV drone technology or more sophisticated monitoring to control those plants. Prospects are also good, like it's 20% in annual growth of the growth rate, so it's exponentially growing, and it's basically very, very cheap and cheap technology and endless use cases. At Volatec, we work with both, as I said before, like PV and CSP plants, both technologies can be inspected and need to be inspected with drones. So this is just a little bit of an idea what you can gain by running a power plant in the most successful manner or most controlled manner. So if you have a 100 megawatt CSP plant, so this is a CSP plant example. It's not that every plant works like this or the numbers are the same, but you can assume in a place like Morocco that this plant produces like 250,000 megawatt hours a year, and this converts to 25 million euros, assuming a price of 100 euros per megawatt hour, which is also dropping over the years. But we see that roughly you can lose, or we see that some plants lose up to 4% in efficiency. So that converts then to €1 million a year. And the very old-fashioned, so to say, inspection, operation and maintenance procedures also are expensive because you have people in the field that walk around or drive around the field and look at everything, every component. That's costly. Also, safety can be an issue. So that sums up to 1.2 million euros a year, which can be saved if you replace that by more sophisticated, automized drone inspections. A typical average assumption that you find in literature is basically half of that, and in PV it's less because PV is just more simple, to put it like simple. So one assumption that I found is 220,000 a year of loss in revenues due to insufficient operation and maintenance. So if you employ aerial inspection in such a field with us specifically, you can gain clarity. So you know what's happening in your field, you know more details on what's going on there, you save resources, so people in the field do not have to walk around the field looking at faults themselves. They win time, they win autonomy. So if you have, this is a special application case of a software as a service, because we enable simple field technicians to fly the drones themselves. So they don't have to coordinate with an external drone pilot. So they can do the analysis whenever they want. And in the end, of course, you improve performance, which in turn increases the profitability of the plant. And that's what actually counts for the operator in the end. So now coming to the technical details of failure detection itself. So first, CSP. CSP plants are vast. So this is an example from Spain where you have like 150 megawatts, what you see in this image. It looks all the same. So if you're driving around that field, you get lost, basically. So what can go wrong in such a field? You have the tube, which has to be accurately placed in the focal line of, or focal point of that parabolic trough. If a mirror is misaligned, that ray is not reflected onto the tube itself, but it misses the tube, and the radiance, of course, is lost. So you need to know exactly where those mirrors are facing and where they're facing wrongly. And we solved this issue, and we can measure the alignment of the mirrors with high precision. So this is in milliradians, and you can see on the color scale, green regions are hitting the tube perfectly, and as soon as it goes into the reddish or bluish direction, then the rays will miss the tube. Also, the tube placement itself, like if it has an offset in any direction, that's something bad. The mirrors can be placed well, but if the tube is not aligned perfectly, then the rays do not hit the tube and it cannot be converted to electricity. Basically, we detect from, this is a drone image actually, so we blurred out the background, so you can only see the parabolic trough, like the mirror surfaces, and you can see this black area, which is actually the tube. It becomes bigger because from far away, the parabolic trough acts like a lens, and you can see those dips here. So this curve here, you can see my mouse correctly. Do you? Yes? Well, on the right-hand side, on the very right trough, you can see that this line is like snaky and shaky. And that means that the mirrors are not aligned perfectly, or the tube just wobbles around a little bit. So this is like a loop effect here, which we use to detect failures. Same thing here. So the concentrator alignment, so if one concentrator here, you have a shift, obviously, on the right-hand side. You can see that the tube reflections are on the left in the upper part of the image and more on the right in the lower part of the image. So the entire collector is misaligned. So it's not tracking the sun perfectly. Then also glass breakage is an issue. You can see it on the left-hand side where there's mirrors missing and you can see the ground below those mirrors. That's another issue which is happening quite a lot in CSP plants. There's many more of those technical parameters that we detect here. These are some of our product packages that we offer for the CSP technology. So the heat collecting elements, temperature, and also advanced analysis, collector package, concentrated geometry, the mirrors and the tube location, torsion, if you have some torsion along a trough, the alignment, glass breakage. And you can then book, in our case, you can book packages of 1 measurement a year, 2 measurements a year, or 12 measurements a year. Actually, some customers are even going higher because they want to track errors and faults as soon as they come up with even weekly frequencies. So that's in CSP. There you can see that the measurement frequency is much higher than in PV. So PV is my next topic here. I'll show you a little bit the working principle of our PV workflow. So as we take images of the field, you can see original images on the left of this slide. We created a digital twin before that. So that's done either during the first flight, like by image analysis, we create a digital twin. But at this point, the software already knows where it has to expect modules. So it knows more or less accurately how the field is built. Knowing that, we can, from the GPS signal together with the camera orientation and some more magic, like we do not rely only on GPS because it's only accurate to a few meters, and a module is just in that range. So there's a big source of error if you only use GPS to miss the module or to say that the fault is in another different module than the one that you say actually. So we need to double that up, not only GPS, but also triangulation of from module lines to know exactly which module we're talking about. So in and the same module appears in multiple images of a measurement flight. We have like 5 or 7 images of each of those modules. We cut them out. We create a so-called ortho image. And then of those ortho images that correspond to one and the same module, we then run the thermographic failure analysis one by one on each of these modules. And then we categorize the errors or the non-errors on those modules. And then we can feed that back into the digital twin. So on the bottom here on the right, you can see our web app where we display, in this case, I think it's soiling, medium soiling, so that's why there's so many errors here. But you can display, let's say, bypass diodes, which is the upper case in the actual ortho images, which you can see here. So that's basically our basic workflow that we apply here for the infrared images, and that in parallel works also for the RGB images. But anyways, some fault types, we've seen them before. So there's hotspots, for example, then you have shading here, which causes a slight temperature increase on the entire string. You have disconnected modules, and all that can be detected. Sometimes you have question marks like this one here, it's a colder string or a colder table within the entire plant. So that's weird because you only see heating up modules, or you can see a hotspot here, but which seems like a normal hotspot. But as I said, we look at the RGB images in the same flight, of the same flight. And here we can see in this case that there was a bird dropping on that cell, which caused this hotspot. So this tells us that the operator does not have to exchange that module, but he just needs to clean it. And it would be a loss of a few €100, including the technician to exchange that module, if he exchanged the module, no? So cleaning is a much easier task, a much cheaper task. And in this case, the colder module, of course, there was a cleaning machine at the same time going through the field. That's why the water cleaned that module. Then another product that we have, I think we're the only ones offering this product on the PV market. That's the soiling ratio. That's something that was developed at DLR by myself, actually. And we have to license that from DLR as for marketing within Volatec. The detection is analytic, still 100%, but of course, we're not omitting including AI methods in this method here. So you need to do a one-time local dust calibration in order to get some images of that kind. Like here in this plant, in this example, some modules have been cleaned, like in the lower row and in the upper row, to produce also clean or contrast to clean modules. And you can see a typical pattern which happens in many PV plants, which where the dust is just washed down to the lower cell string or cell level here. So we can actually measure entire solar fields, the soiling distribution over entire solar fields. The accuracy is, well, absolute. It's hard to quantify, but the main reason why it's hard to quantify is because of the reference measurement. So the reference measurement for soiling is, not so reliable. And so we say that we specify by 2%. We're really good when comparing soiling levels within the same field. We don't know all too much about how the absolute value corresponds to the actual losses for soiling, but they're quite good still, or at least we're confident. And we measure that on the cell level. So that's also one advantage over other devices that are on the market. So in PV, we offer 3 packages of products, basically. So first, according to the standard, that's basically flying at below 20 meters, just below 20 meters to get the right resolution. The survey is enough as of accuracy for most of our clients. So it's flying at 40 meters altitude, and PV soiling, usually from the flying, it's the same flight routes. You can use the same or just one flyover of the field, and you get the PV soiling package also. And you can fly yourself, with a pilot, with some solar field technician, buying your own drone. Then you're autonomous, or we're about to launch our drone in a box package. So we're working on this. We have a test running. I'll come back to that later. So AI, so that's the topic here. Our foundation of the analysis is all analytic. So we started off analytic. We have a very profound and deep knowledge of image analysis, which is basically all analytic. But of course, AI, we don't want to discard it, and we're including it at specific and well-defined points. Mostly where we see that we have to interact as the programmers before handing out the data. We had to review data. We had to correct some details in the analysis, in the results. And that's one of the main points where AI has helped us a lot. And also, we want to improve performance at specific points. We can increase the accuracy at specific points, but we still want to be in control of what the AI is doing. So that's why we decided to choose the best of both worlds, to not have a black box with just a training data set, which somebody labeled, and then you cannot improve the entire thing at specific points. And we still don't want to, we still want to profit from this potential of AI at specific points in our workflow. So that's basically our philosophy of implementing, of integrating AI into our software here. And we see great potential. So it's not about saying that AI is not good enough or something. We just don't want those black box. This is for us one of the major arguments to still have the basic analytic workflow running in our case. So how does it actually work? If you're a client, how do you actually measure with us? How do you get first measurement results? So step 0, it's up here, it's on the left. We need to know where your panels are. We need to digitize your plant. So we need to create a digital twin. This can be done either during the first flight in the same flow, or we just have a perimeter in Google Maps, and then this can be digitized. So there's various models of how to do this. But once this is digitized, it's just one time. Then you can repeat the other steps as often as you want, which is, of course, you need to acquire the data. This usually works with the client itself, having bought one drone and having somebody in his team who can fly the drone. Then the data analysis happens that's our job, basically. We provide, of course, the pilot with the flight routes. They are designed based on the digital twin. So we do the analysis, and then you can view the data in our web app, where I come back later also. So you get health reports, you get actionable steps for optimization, and of course the feedback here from our clients is invaluable. What they're looking for and what they actually use and what they make of our data. So how do we digitize this? So from Google Maps, we have software that recognizes panels and strings of panels and tables, and then converts it to a layout plan of this PV plant. So the software knows where to expect panels. How does the data acquisition work? Well, we have several ways of connecting or of transferring a flight route to a controller or to a drone in the end. So for DJI, we can use the DJI is a manufacturer of drones, so the most known manufacturer. We can upload the DJI, the flight route directly to your DJI account. So you can use that directly, or you can use Litchi. And we also built our own Volafly app, which can be uploaded to the controller, which is nice because it's easier. Like our intention is to make it as easy as possible for the user. And here, all the camera settings and stuff is already preset in our application. And in the other 2 applications, you need to do it your own, which is not a lot of steps, but still there's some source of error here. For flight parameters, flight height is between 15 and 40 meters in photovoltaics, a lot higher. It can be a lot higher in CSP. Flight speed is 5 meters and 10 meters. And image overlap is also one question that we get a lot, but we're working with videos. So we take videos and then we can just chop this video into separate images and then define the overlap ourselves or control it ourselves after the flight. And we use, of course, the DJI tools, which are really nice in terms of anti-collision and flight restriction zones. Once you've flown your drone, then you need to upload the data to our portal. So that's how that looks. It's pretty easy. Just need to select your plant, the acquisition date, and then upload that. And you can also, in this portal, you can also, if you want to do another analysis another day, you can also require, or on demand, you can demand your new flight routes for that day. This is the results presentation. Then you have a map, basically. Errors show up in color. So this is a CSP plant, if I'm not wrong. Yeah. If you click on something, then you get all the details shown in a pop-up window. You get some statistics and a legend on the left. you can switch to table view, statistics view. You can get a history of measurements. And of course, we have all the transfer protocols installed to like integrate our measurements into your plant measurement management tools. But you can use our software also as a plant management tool. So add own observations, take an image if you're in the field. And of course, if you take your device into the field, like a mobile tablet or even a mobile phone, you walk around just like in Google Maps. You can see your blue dot where you're walking, and you can turn around and you know that you're looking at the fault that we detected. And this makes it very easy to work with. And there's also an offline mode, which is an issue in many plants where you don't have stable internet. You can just download the results and then walk around anyways and have everything available without stable internet. So to sum it all up, we provide very high level of automation because you can just repeat that. The flight routes are automatically created, and yeah, it's very automated. And you can be independent. You do not need to call in a pilot. We just have our software, and we do all the rest. We have, yeah, quite a nice way of presenting the results, and it can be applied by anyone. It's actually dead simple up to now. And it's an all-in-one solution. You can, of course, apply it globally because it's just software. So where we're going, drone docks is a big issue for us, or a big topic for us. We're just testing a few different models. CSP has, like in CSP, there's a bigger potential of application of drone docks, docking stations, totally autonomous drones. And then in PV, you have to look for the application cases, but large plants or high loss rates are, of course, some of the target areas. And then other development lines, like we're collaborating with a company where we actually want to fully integrate our inspection results to a monitoring software in PV. And we're working on applications for agri-photovoltaics, where we combine crop health monitoring with thermography. We're used to complex geometries from CSP. So as soon as you have PV installed in complicated buildings or something, that's something where we are at home. And desert climates is also something where we learned a lot in CSP. So that's these things we want to bring into the PV sector as well. And of course, we're open to any kind of partnerships, cooperations, and research. Yeah, that's our team. We're growing, so there's even actually two persons that are not in the pictures here. Yeah, so that was it from my side. I'm happy to answer any questions.